Hello everyone and welcome. My name is Sari Sabasadia. I'm a PhD candidate at Michigan. This presentation is for the paper EEG channel interpolation using deep encoder-decoder networks, presented at the 4th International Workshop on Deep Learning in Bioinformatics, Biomedicine, and Healthcare. It is in the 2020 International Conference on Bioinformatics and Biomedicine. This presentation will begin with a short background segment to provide necessary context. We then move on to discuss our methodology of experimentation, and finally we'll have a short demo to showcase the software that comes with our presentation and how you can use it. First, however, I would like to acknowledge my collaborators. I was fortunate enough to be able to work with Professor El-Hani from NYU at Abu Dhabi, as well as my two advisors, Dr. Liu and Dr. Ghassini. Without their support, this project would not have come to be. So, today there are dozens of commercial EEG setups, for instance, Emotive or OpenBCI, and hundreds of applications for these setups are readily available on GitHub. However, if you ever actually downloaded one and played with it, you discover that it's somewhat buggy. Even the most simple applications like Space Invaders do not really work that well. This is not particularly surprising for anyone that worked with EEG signals before. They are notoriously noisy. And today we focus on one specific artifact that contributes to this low signal-to-noise ratio, the pop artifacts. Electrode pops are the most common type of artifacts. They originate from a spontaneous loss of connectivity between the scalp and an electrode. In EEG signal, it simply looks as if the signal is maxed out or minimized all the way down. Unlike muscle and blink artifacts, there is really very little the experimenter can do to mitigate this type of artifacts. Moreover, a lot of artifact detection algorithms, such as those that are based on independent component analysis, ICA, do not work unless the data is free of electrode pops. So, in a sense, you need to make sure that you either discard trials with electrode pops or correct the electrode pops before you do any other type of artifact detection. So, considering all of this, it's not surprising that quite a few people suggested algorithm to interpolate these channels. Perhaps the most common channel interpolation method that actually comes with EEG Lab out of the box was proposed by Perrin et al. At the late 80s, and it's the spherical spline method. We hope that our work can be useful for anyone that's looking for a more modern approach. So, our method was inspired by a computer vision problem, image painting. Basically, given an image with a corrupted or missing pixel, you want an algorithm to be able to fill in the pixel or just approximate its value. So I'm sure that the similarities between this and EEG channel interpolations are quite straightforward. So by presenting EEG as a time series of topographically organized images, where we spatially organize the different channels, we are able to get a self-supervised deep learning kind of framework where, given trials that do not have electric pops, we can decide to include a specific channel. For instance, in here we include the F8 and give the original image, the included image, to our model as the ground truth. This brings about quite a few interesting implications. First, there's really no need for any kind of human labeling. Pop artifacts are very easy to detect. Again, it simply looks like the channel is being maxed out. So we can easily get only clean trials that we have no doubt do not have a pop artifacts. Secondly, unlike other interpolation methods, we do not need any kind of specialized metadata, such as the exact electrode locations. These can be learned by the model itself, how to optimize the weights of the different channels when interpolating the specific one. Third, we can leverage different strengths of deep learning, such as transfer learning, to improve performance on datasets that were not available during the training and design of this algorithm. So, to make sure that our work is as useful as possible, we want to make sure that it generalizes across different subjects and tasks. So we use the mental arithmetic dataset from PhysioNet, and we segment it into 4 different sub-datasets. So the original dataset has resting state EEG data as well as mental arithmetic data. We also segmented the subjects, and we get this 4x4 seen task, seen subject, unseen task, unseen subject, and both subjects and tasks that are not available during training. In the first phase, we only train the model on the seen task, seen subject, so resting state data on 16 subjects. We use 90% of that data, and we test on the remaining 10%. And we also test the performance on data from the 3 other datasets that were not available during training to make sure that our algorithm generalize well. In the second experimentation, we use transfer learning using 10% of the data in the 3 datasets that were not available during training. And we checked if using this 10% we can tune the network further to improve the performance on these datasets. So our architecture follows previous image imprinting approaches and some EEG artifact detection work. It's a convolutional neural network, encoder-decoder. For the interest of time, we will not delve too deeply into the architecture, but please see our paper too for full description. So, as you can see, our results were quite encouraging. The encoder-decoder model did outperform all of the traditional baseline methods that we tested. Moreover, when we used transfer learning, we saw an even more significant improvement. This has quite a few interesting takeaways. By the way, the numbers are all in mean square error, so lower is of course better. So the first and obvious takeaway is that deep learning is in fact a successful EEG channel interpolation method, and moreover, deep learning can be used in a generative fashion for EEG data. A lot of previous people that use deep learning for EEG used it discriminatively, meaning just to detect the artifacts. We show that you can use it generatively to also generate corrected EEG data. And of course, it's better to correct instead of just detect and discard trials that are artifact-driven. Secondly, we show that deep learning, when designed carefully, can generalize across different subjects and tasks. Other works that worked on very similar problems did not really test how their methods generalize, which kind of calls into questions the usability of their methods. But it seems like EEG can, in fact, not suffer from overfitting if you are careful. Finally, and perhaps most interestingly, transfer learning is perfect for learning small idiosyncrasies that happen in different tasks and subject setups. This is a powerful tool for researchers working with any kind of human subject data that is idiosyncronous by nature. We hope that our work can inspire a greater use in EEG for data preprocessing and normalization. Okay, welcome to the demo part of this presentation. This IPython notebook example can be found in the GitHub. So the very first thing we do is, of course, we load everything that will be used, and then we make sure that we are in the correct location. So the model directory would have the topology and the weight of the model that we have found is the best performing one. So you can simply load them, and you can look at the architecture of the loaded one with all of the pre-trained weights. You can also load the class baselines from our baseline folder. So I'm going to use data from a separate experiment that I've been working on. It's an EEG lab data. So the way EEG lab data looks when you load it into Python is basically like this. These are all of the channels, and you can also look at the data. So this was collected using the 21 standard international 1020 electrodes, and it has 91,000 samples. So you initialize the baselines class with an org data, and this creates an instance of a baseline class that has the specific electrode locations and then electrode names that the data that we loaded had. So you can choose to normalize specific epochs in the data. We're going to take the 40 to 50 epochs and just normalize them, and we'll get the EEG data. So the normalized EEG data is 1, the data itself is normalized. 2, the shape of the data is an 8x8 tensor, so it already broadcasted it into an 8x8 and took only 8 samples. You can look at different trials that we got, which is what our neural network expects. Additionally, the baseline has the occlude method that would simply occlude the data. So if you look at a sample of the original data, you would see that by looking at the same data and the pop data, the only difference is that one of the channels not occluded. We are occluding the channel 3.3, which assumes the central 0 electrode. So the baseline also can use interpolations that are more common in the literature. So this is the Euclidean, and EGL is an interpolation method from 2016. And you can get the interpolation method from our network simply by using the predict function with our pre-trained neural network. You give it the pop data, and the blue one is the original data, the red is our interpolated data. As you can see, our interpolated data is much closer to the original. You can also, instead of just looking at one, look at more. So this will take the first 5 and simply stack them. And this means that instead of just 8, it is 8 times 5. And remember in here to also say 0 to 5, and we need to flatten it now because it will be a 2D array. Flatten. And as you can see, the other methods have these spikes that are not in our reconstruction. So our reconstruction has a much better fidelity to the original EEG data. You can also, let's do 2030, just since we're already here. And again, you can see the original one and the spikes in the other methods from other channels that we do not have in our reconstruction. We hope this was useful, and please contact us with any further questions.